This is the first recording of battery design. I'm just going to go through the basics that applies to all batteries. The ideal battery, we would be able to just store and retrieve electricity at any rate that we want to put it in and take it out, be 100% efficient and lightweight. No such battery exists. The reality is that batteries are heavy, and the weight of the batteries is one of the main reasons that we're not driving electric cars today. They also are bulky and they take up a lot of space. Batteries are inefficient. If you get back 80% of the energy that you put into charging the battery, that's pretty good. And the efficiency depends on how fast you want to put the charge in and out of the battery. There's some terminology that we need to understand here. Energy density is watt hours per kilogram, how much energy for the weight of the battery. The amp hour capacity of the battery, that's an amp hour is 3,600 coulombs. So this is just basically how much charge we can put into the batteries. The watt hour capacity is the energy that we can put into the battery. So, amp hour capacity and watt hour capacity are a little bit different. And then there is the C rating for the battery. And that's how fast we want to charge or discharge it, because we find especially the watt hour capacity of the battery depends on how fast we charge and discharge it. So a C over 3 means we're going to completely charge or discharge the battery in 3 hours. A C over 8 would be in 8 hours. There's two kinds of efficiency. The charge efficiency is how many amp hours does it take to charge it, and how many amp hours does it take to discharge it, and or how many amp hours we get back when we discharge it, and we ratio them. The batteries that we are interested in for electric vehicles will have a very high charge efficiency. You'll get almost all of the amp hours back out that you put in. I mean, that's Coulomb charge, very little loss. The second law of thermodynamics says there has to be some loss, but it's very small. Now, energy efficiency, we ratio the energy required to charge the battery and the energy that we get back from the battery when we discharge it. The energy efficiency is not 100%. To help understand why it's not 100%, this is a charge and discharge curve for a typical battery. So when we charge it up, we have to go to its voltage on the y-axis, and across the bottom is the charge. You can think of it as Coulomb charge or amp hour charge, but completely discharged on the left and completely charged on the right. And we'll start out charging it at a voltage. The voltage will gradually increase as we get closer and closer to full charge. And when we get really close to full charge, it'll even kind of increase at a faster rate. And then when we take that same battery and we discharge it, we start drawing current out, the voltage will drop below where we were at charging the battery, and we'll discharge it. And when we get close to complete discharge, the voltage will really fall off a lot. Now, energy is voltage times charge. 1 joule of energy is equal to 1 volt times 1 coulomb. So the area under these curves represent energy. And you can see from the graph that the area under the charging curve is always larger than the area under the discharging curve. So the energy efficiency is less than 100%. Ideally, we'd like to charge and discharge and keep these two curves pretty close together so that we have a high efficiency. But what we're going to find is, it depends on how fast we want to charge and discharge. So I said a lot of this on the previous chart. Voltage times charge is energy. And now once we recognize that the charge efficiency, we're going to get pretty much all of the charge out of the battery that we put into it as far as the amp hours charge, then really it's a ratio of the voltages that determines the energy efficiency of the battery. The voltage we have to charge it at versus the voltage that we discharge it. And efficiency is low at low states of charge because the discharge voltage gets low. The efficiency is low at high states of charge too, because the voltage required to charge it is high. And we also have to reduce the rate that we charge. And it's in the middle that we really get the best efficiency, between about 25% and 75% charge is where we get the best efficiency out of the batteries. Now, we need to talk a little more in detail. We need to talk about open circuit voltage of the batteries. To achieve open circuit voltage, you have to let the battery sit for a while. And for a typical large lead acid batteries, you've got to just let it sit for a couple of hours. It has to achieve chemical equilibrium, and the chemistry that's going on inside of the battery has to stabilize out and reach equilibrium. Then you can go in with a good quality voltmeter and you can measure the open circuit voltage across the positive and negative terminal. The open circuit voltage will vary with the state of charge, and if you let the battery stabilize like this and give it a couple hours to just sit there and stabilize, you can directly relate the open circuit voltage to the state of charge, how charged the battery is. The thing is, open circuit voltage doesn't vary a lot, and it is very sensitive to letting the battery stabilize. And so it's not always the best way to measure how much charge is in the battery. In order to push current into the battery, we have to go above this open circuit voltage. If we just apply a voltage equal to the open circuit voltage, no current will flow into the battery. And so charging the battery, we always have to go above the open circuit voltage. The faster we want to charge the battery, the higher voltage we have to go to push the current into the battery. When we get close to full charge, then the chemical reaction is almost completely done. And you have to reduce the rate because there's just not a lot of place left for this chemical reaction to occur, and you have to slow down the rate as you get to full charge or you'll damage the battery. In order to discharge the battery, we have to go below the open circuit voltage. We have to draw it out. If we do not go below the open circuit voltage, no current will flow out of the battery. So, and the faster we want to draw it out, the lower voltage we have to draw it out at. And as we get close to full discharge, the chemical reaction in discharge is almost complete. We have to slow down the reaction rate or we will damage the batteries. And that's the way it is. This chart helps us understand how the efficiency of the battery is going to be impacted by the charging rate. Because for slow charging and discharging, we go just a little above the open circuit voltage to charge and a little below the open circuit voltage to discharge. But to go fast, we have to go a lot above the open circuit voltage to charge, and we have to pull it out at a lot below the open circuit voltage. The chart also illustrates how if we start with a fully charged battery and we discharge it slowly, the area under the curve is a lot more than if we discharge the battery quickly. And so when we start trying to say how much energy is in the battery, it depends on how fast you want to draw the energy out of the battery. So you can't, it's not like the gas tank where we can just say, there's 10 gallons in the tank or whatever. But the amount of energy in the batteries depends on how fast you want to draw the energy out. And I think it's probably obvious to most of you, but it's most efficient if we charge and discharge slowly. And If we go with a larger capacity battery, for the same power draw, we'll probably have a little bit better efficiency. And this gives you the basics of how batteries work. And I'm going to go ahead and pause here to break up the recordings a little bit.